I hope that my talk is going to be fairly easily digested. So my plan is not to attack you with lots of heavy math. So but still I would like to present the subject that I'm really interested in, since basically I did my PhD and I'm still working on it now. I mean, in different aspects, of course. So that being said, I would like to start from introducing you one of the simplest dynamical systems that I have in mind, that it's usually being introduced as one of the first examples. So I'm talking about billiard system, right? So you can see a billiard. So what is a billiard? So billiard is some kind of very simplified dynamical model that is supposed to model some easy behavior, such that some physical behavior, such as a ray of light reflecting off a mirror in a room of mirrors, or perhaps a motion of a gas particle inside a container. But like I said, the model is very simplified. So we are just going to consider 2D model of that. And actually, I'm going to consider a 2D. So first, when we're talking about billiards, we need to choose our table. So I will start from a simplest table. I will start from the rectangular table. So as the one that you can see here on the picture, but maybe, yeah, let me pass to a very simplified model. So we have a table like that, right? So this is a billiard table. The red point is our ball. And we assume many simplifications. So we assume that the ball moves in a fixed direction with a uniform speed. And whenever it hits the corner, it stops, okay? Whenever it hits the corner, it stops. And when it hits a wall outside of the corner, we assume that the angle of incidence is equal to the angle of reflection, okay? Now this is a very simple, and this is called the billiard flow, such dynamics. And it's a very simple model, as you can see, but okay, we would like to ask some questions, for example, like we would like to ask whether the ball will hit approximately every point in the billiard table, or maybe it is actually going to be a periodic orbit, right? So what can we do? Okay, so we could study the orbit as it is. So we could study a very long orbit and just record the position of the point. But there is one issue. I don't know, it's not a very complicated issue, but the problem is that, okay, once we have, for example, this rectangular billiard table, then, okay, so we not only have to record the position of the point, but we also have to record the direction. So actually our phase space in case of rectangle is going to be, okay, the points in the table, but also the 4 possible directions, okay? Maybe it's not a problem, but for me, it's a problem and I would like to deal with it. I would like to have one direction. So what can I do? Okay, and the issue, the solution is over here. So it's written over here. So instead of reflecting the ball of the wall, the standard trick is reflect the table. Okay, so everything on the paper, it's easier than in the physical world. So let's do it. So we are reflecting the table, and what we are going to get, I hope, is presented over here. Okay, so the blue point, the red point is our ball, and the blue the blue line is the orbit, right? So with fixed direction, we hit the ball, and normally when we would reflect off the wall, with keeping the rule that the angle of incidence is equal to the angle of reflection, I mean, we would get a broken line, right? So the blue line will become a broken line. But instead, what I'm doing is I'm reflecting the table, which I hope, as you can see, so I put in the rectangles some green triangles, which are supposed to tell you that more or less what is the orientation, what is the what is the direction that corresponds to the table. But so as you can see, so what is happening? So suddenly my problem gets a little bit simplified because I don't get a broken line anymore. So my orbit now becomes a line, right? So it becomes a line. And then if I consider, instead of a finite table, an infinite surface, right, in which I unfold my table, I can study my orbits as straight lines. And straight lines are arguably easier to study than broken lines, right? So if I want, for example, here in this picture, you can see that I would like to find a periodic orbit. So I would like to find a periodic orbit. So there are very simple periodic orbit for which I do not need this such a picture. So for example, if I hit my ball parallelly to the sides, then it's just going to bounce off the sides infinitely many times, right? Assuming, of course, that it never slows down. So there is no friction, and this is also what I assume. Now, like I said, it's a very simplified model. But for example, if I want to find more complicated periodic orbits, so as you can see this skewed blue line, right? So the only thing I have to do is I have to consider my unfolded table, right? And look for two copies of the point in which I have started. So I have a point in the lower bottom corner, and I have a another copy of the same point, right? I have to take care so that the triangle, the green triangle, which tells me in which direction I am considering, is the same. So I'm considering another copy of my point, and I'm just connecting those 2 points with a straight line. And that's it. I have found a periodic orbit. And I can do it infinitely many times. So I can find as long periodic orbit as I want. And then I can study this problem. Okay, this is a very easy problem to study, but it tells you that, okay, that this method at least helps in one issue. Okay, so but now the thing is that my picture has become infinite, right? So now I have to deal with an infinite flat surface with R2. I don't like infinite, right? I would like to see a finite thing. So what can I do alternatively? Well, instead of just considering all the unfolded tables, I can consider just the copies, single copies that correspond to single directions of the ball. So just in this case, it's just going to be 4 copies. So you can take a look, for example, let me see. Yeah, so I took the 4 copies which correspond to the direction. And instead of unfolding this copy further, I've got all the directions that are possible already in this picture in the form of those 4 copies. So instead of unfolding further this picture, I can just teleport myself whenever I hit the wall of one of the copies to the copy that corresponds to the direction that that I would obtain normally by reflecting. So you can see what it is. I hope it is visible over here. So we start. This is the periodic orbit from the previous picture, but still I start from the red ball. I'm moving in the direction, right? I'm moving up to the right until I hit the top wall. And then what do? I instead of unfolding. So normally I would get the copy, another copy of the lower bottom copy again of my table. But instead I'm going to the copy that I already have by teleporting. So this teleporting has a name, of course, in math. I mean, this is just a translation, right? So what I'm doing is I'm actually identify the top side of my picture with the bottom side of my picture by a simple vertical translation. And the same thing goes for the left-hand side and right-hand side sides of my table. I'm doing the same. Of course, I have to use different translation, but still I'm doing that. I'm gluing those sides via translation. And what do I get? So okay, so now my picture is finite and my orbit is still a straight line. Okay, but okay, so from the orbit point of view, so for the point of view of studying my billiard flow, I am very happy. But what object did I actually obtain in this way? Well, the object that I obtained in this way is going to be actually a torus. So once I take a piece of paper and I connect the opposite sides of my piece of paper and I glue them, then what do I get? I get a torus. So I get a genus 1 surface. So actually, I translated the problem of studying billiard flow into studying exactly translation flow on a translation surface, which in this case is a torus. So I have a surface and I move in one fixed direction with a unit speed. And this is the object that I want to study, not only on the torus, but also on the other surfaces. So to motivate a little bit, I don't want to get more into details of more complicated billiards, but for example, yes, so what was very helpful in this unfolding picture is that the square or the rectangle has all the degrees 90 degrees, so we get the tiled surface, right? But I'm not only interested in rectangular billiards. So the same trick would, for example, work if I took a regular triangle and I consider it a billiard in a regular triangle. But what if I want to use other polygons, right? So I can do exactly the same, but what is happening is that you need to use a little bit of imagination, and you need to imagine that you are unfolding not one, but many surfaces. It may happen that you need to use many surfaces. So what I would like to, okay, I don't know if it's going to be convincing, but let me show you the picture for the regular pentagon, for example. So we start from the left-hand side, from the left top corner, and then we unfold around the vertex. So we are basically assume for simplicity that instead that we are reflecting, not say with a straight line. I'm just interested to see how the table is being reflected. And as you can see, basically, so I colored the red line. So this is the line that we would like to understand when are we returning to this red line. And as you can see via the reflection around the sides, which are glued to this one, which come out of this, of one of those vertices, one of the vertices of the pentagon, I'm actually accumulating layers, right? Because the angle of the regular pentagon is not, it's 180 degrees, right? So it's not, it doesn't divide 360 degrees. So you actually, when you say, for example, glue three of those triangles, three of those pentagons, right? In the third picture, you can see that we didn't do the whole, we didn't did like a one rotation, right? So we didn't do one rotation. We did like a almost full rotation, but we don't care about it. We add another, we reflect another pentagon, and then we obtain this yellow trapezoid. And what we do? Do we worry? No, we don't worry. We just reflect further. Okay, so we reflect, and then we get another layer, and until we are doing the third layer, we go back to our initial with the position of how we recover the position of our initial interval. Okay, so we obtain a much more complicated picture. So actually, if you count, we actually have we added 10 copies of pentagons, of a regular pentagon, which is natural because if you think about it, when you play billiard in a regular pentagon, you have a 10 possible, once you fix direction, and you want to consider all the possible direction that you can get via reflection, it appears that you have 10 possible directions. And then actually you can do the same trick. So you can also consider those 10 pentagons and glue sides to which you teleport via reflection. And it turns out it's not that easy to see, but you can find it in the literature that you actually also will obtain a surface, but this time the surface will be of genus 6. So it's a way more complicated object than a torus, but still the billiard flow, in pentagonal billiard flow on the surface now is going to be again a flow in a fixed direction. And we refer to such flow as translation flows. So now with this introduction, I am ready to introduce more formally, maybe, but more the object that is of my interest. So these are called translation surfaces. Okay, so what do? We take our Cartesian system, Cartesian plane, and we start from 0 and we draw, we want to draw a 2D gun. A 2D gun. We are doing this in the following way. So we first draw a broken line consisting of D intervals, but we demand that this broken line lies on the upper half, starts from 0, moves to the right. So it gives you some restriction on the intervals, and also we would like to keep it on the upper half plane. Okay, and this is, I hope you can see on my picture. So we see the upper, so we have the red interval, green, purple, blue, yellow, and brown interval, right? And they form this curve in the upper half plane. And then what do? This is not a polygon yet, but we want a polygon. So what do? We now add the lower broken line. The lower broken line consists of the translated copies of the intervals which were making the upper curve. Okay, and I hope you can see it, but of course, but now we want to keep the lower curve, I'm calling it lower curve, we want to keep it on the lower half plane, okay, on the lower half plane. So we cannot take the same order of the intervals. So as you can see on my picture, I first took brown, purple, green, yellow, blue, and red. Okay, and now I have a, of course, since I'm just shuffling what is essentially vectors. So the sum of vectors, I mean, the summation is independent. It doesn't depend on the order of summation. So we should get back to the same point. So this condition of being on in the upper half plane or lower half plane does not include the rightmost intervals. Otherwise, we would have nothing we would have no such objects. Okay, so now we have a polygon which consists of lower and upper curve, and each of those curves consists of D intervals, and we have D exact copies of each intervals. And now, as you saw in the case of the torus, what did we do is we were gluing the upper and lower side via translation, and left-hand side and right-hand side as well. And we do it exactly like that over here. So we simply glue the intervals on which have the same color, they are the same copies. We glue them via translation, okay? And we get some kind of surface. We get some kind of surface by so for example, if there were 2 intervals, then we would get a surface of genus 2. Sorry, a surface of genus 1, we would get a torus. It seems it can be checked that if you take 3 intervals that we also get a surface of genus 1. But if you take any higher number of intervals, you can actually get any genus. You can get a surface of any genus, any finite genus that you want, basically. Okay, and but there is no dynamics yet, right? And we want to consider dynamics. So what will be the dynamics? So we simply do what we did in the case of the billiards. So we fix a direction and we just move with uniform speed in this direction everywhere. And this is my flow. This is my very simple object. Here I should have another picture where you can see another surface. Another surface. This consists of 4 intervals, and you can see a very big clumsy arrow that tells you like which direction you are moving. Without any loss of generality, we typically assume that we always think that the direction of the flow is vertical, just for simplification. There is a little bit lie over here because not always you can do that, but the cases where you cannot do that actually it's proven that they are very, very rare. So just believe me that you can do it normally for most of the surfaces. You can think of them as the flow is vertical and it's vertical up. Okay, so here I also have colors that tells you which intervals are glued to each other. And I also have to maybe point out something that, as you can see, that all the vertices in this in my picture are actually labeled as 1, so they are labeled in the same way. And you can think, okay, why am I doing this? Why do I? Is this a typo? Is this a mistake? No, it is not a mistake. It's not a mistake because when you are actually gluing the intervals, I mean, in particular, you're gluing also their endpoints. But it seems that the endpoints are common not to always to 2 of those intervals. And it seems that after you glue them, some of them might get identified. So some of them may actually be glued and become 1 point. And this is the case exactly in this picture. So in this picture, if you think, if you, for example, would like to know, this is also interesting. So you take this point, so you take one of the vertices, and you would like to understand what is the full rotation around this vertex. So like I start in any point and I'm starting to rotate around this point. And how much angle I actually do. So it turns out that in this picture, because we have all those gluings, so for example, we start in the, say, around in the red, in the top left vertex, and we start moving anti-clockwise from the red interval, then we go to green interval, then we go from, because since everything is glued via translation, we go to the green interval at the bottom. Then at the bottom, we rotate around the blue interval. And then everything is glued via translation. So we go to the top blue bottom interval and so on and so on. And it seems that actually you will travel through all the vertices of your polygon. So actually the full rotation around this vertex, it's not 2 pi, as usually, it's 6 pi, okay? So we say that this is a singular point of our translation surface. And it corresponds roughly in the billiard picture to the corners of the polygon. So what is the safest thing to do? So since I am going to be considering my dynamics from the measure point of view, I will explain more of it later. But what do we simply do? We just stop. We just we go there and we say the flow stops, and that's the end of the story for those points. But this is going to be just in the Lebesgue measure, just a 0 measure of points. Okay, so we have this kind of picture. And what is the parametrization of translation surface? I need to tell you about parametrization because I want to state results in the language of parameters. I want to say what does it mean to consider a lot of translation surfaces. Okay, so we have d parameters so we have d intervals, so each of them has a vertical and horizontal parameter. We consider them separately. And we also have permutations, so we don't have to give, since we know that we have d identical pairs of intervals, so it's just enough to give you the parameters of the intervals and then just describe how do they get translated, right? So in this case, for example, we have 4 intervals. So I have 4 vertical, 4 horizontal coordinates, and I need a permutation to tell me how do I get from the upper curve the lower curve. So now I just need the order of intervals. Nothing else is needed. And these are the parameters, and these are the parameters of the surface unit. It's useful to assume some non-reducibility of pi, but I don't want to get into details. You can imagine that not all pi's are good because you somehow don't want to divide your surface into 2 parts, but this is not that important. And here I'm saying, so lambda is just the horizontal vector, so it's a positive vector of positive coordinates. The vertical parameter comes from the mysterious space theta pi, but this mysterious space, okay, it's given by this condition, but this is just the condition which I told you that we want the upper curve to be in the upper plane and the lower curve to be in the lower plane. There is nothing deeper than that, and it seems that so we have both of those. So we have a set of permutations, which is a finite. So it's some discrete amount of points, and we have some d-dimensional subsets of Euclidean space. And when I say typical, I will either consider the measure, so it's going to be a product of the counting measure on the set of permutations and Lebesgue measure on my Euclidean space, or if topology, then it's just a product topology, discrete product of discrete and product of the standard Borel topology given by open cubes. So this is nothing fancy here, but this will tell you. So if I'm going to tell you that something holds for the full Lebesgue, for full Lebesgue measure, for example, I mean this measure. If I would consider like for G delta dense set, I mean with respect to this topology. Okay, so this is something to keep in mind. And also, I want to tell you, not maybe formally, but you might have noticed that a single surface has more than one representation, right? So as you can see in the bottom picture, as you can see in the bottom picture, we can cut one of the triangles, for example, in the left-hand side picture, and glue. So we cut this triangle with purple and green line, and we glue it where the purple line was, right? So on the other purple line copy was, and we just move it via the translation. But the surface didn't change. It's just the picture that changed. Okay, so the surface is the same. So every dynamics, every topological properties, I can give that a distance on this surface. The distance would remain the same. Everything stays the same. So a single surface can really have more than one representation, and we often we divide by this relation. So we divide in the space of parameters. We glue the points that represent the same surface. But this is not going to be that important to understand what's going to happen next. But what is the most important I want to keep you in mind, because it's going to be useful later, that a surface can be represented with a picture usually with different permutations. So we have so there is a whole class actually to a given surface, you can think that there is a whole class of permutations with which we can get a picture in which this surface can be represented. And this class is going to be called a Rosy class. In general, and it cannot be represented by any permutation from outside this class. So there is a natural class of permutations which you just have to consider for your given surface. I mean, if you know more about dynamical systems, you've probably seen the picture that is below. This algorithm is called actually Rosevich induction, and it's a very simple argument with a very non-trivial properties. But it is not the time to talk about that. I want you to remember just the permutation part. Okay, so we are going back to the translation flows. So our translation flow formally is just a family of automorphisms, TT, where T is a real number, and it's just since we are moving with the unit speed upwards, so it's we are just adding locally to local coordinates translation by T, where T is the time, right? And whenever we hit an interval from the upper curve, we translate to its copy in the lower curve. So for example, in this picture, right, whenever if I continue with this arrow that I drew and I will hit the red line, I just move by a translation to the lower copy and I go upwards from over there, and then I hit probably the black interval, and then I go back to black interval, and so on and so on. Okay. So this is the flow, and I will consider a Lebesgue measure on my surface. You can think that it's just the Lebesgue measure restricted to a polygon for simplicity, and you can see that actually if you consider a square when you translate it for a small amount, I mean, it's still the same square, just translated, so the area of the square is the same. But even if you take the square and you hit the discontinuity, so part of the square goes to one part of the surface and the other goes to another part of the surface, the total area of those two copies will still give you the area of your original square. Okay, so this is what it means that the flow preserves the Lebesgue measure. So now I'm always consider, so actually a measure preserving flow should come with a measure that's being preserved. In my case, it's going to be a Lebesgue measure. And this is what I already said, that whenever we hit the vertex, we stop, but the points where we hit the vertex, they form a zero Lebesgue measure set. So from my point of view, they are not that interesting, although they are interesting from other points of view, but everything is interesting. But for now on, you can think that they are not interesting. Okay, and now I need to tell you something about I want to tell you about interval exchange transformation. So if you so the definition of the interval exchange transformation is over here. So it's like we consider a horizontal interval starting from 0 and go rightwards for as much as we need. So for the length of the horizontal, so some of the horizontal parameters. Okay, so we go rightwards, and let me see if I have a picture. Yes. Okay, I don't have a picture, but okay, assume so it's going to go along the x-axis basically. In my picture, I have to take a little bit of a copy that goes through the black part and goes to back to the black part. But as you can see, so and we consider this interval, and what we do. So, and we, instead of considering a flow, we just focus on the points on this interval, and we see when are they going back to this interval. And it seems, and you can, it's not easy, it's not hard to believe that if you don't hit the discontinuity, if you take 2 points from the interval and you don't hit the discontinuity between them, then you are going to return to this interval basically as you were. So if you were distanced by, say, 1/1000, you will return by 1/1000. Okay, so basically this return map is going to be actually, it's going to be an automorphism of the interval, and it's just going to be locally a translation. So the only thing that is going to be more interesting is when you hit actually the discontinuity, because then you actually get the discontinuity of this return map. And this is exactly what is the interval exchange transformation. It's given by the parameters, the same that you got for the surface minus the toss. So you just need the permutation, you just need the length. And then you can see in my picture below that basically you take the interval, you cut it into, say, d copies, and you just shuffle the intervals. And this gives you an automorphism. And you can see that it also preserves the Lebesgue measure. If I take an image of any set via this transformation, if it doesn't cut into pieces, then just a translation. If it cuts into pieces, still those pieces together will give me back my original measure. Okay, and still when as before, when I'm going to talk about typical IETs, I mean typical in the set now of the lambdas times the set of permutations. Okay, and now finally, okay, so this was maybe too long of an introduction, but finally I can tell you what I am personally interested in. So what questions I want to answer about those objects. Okay, so first problem, I will go chronologically. So this was what I already considered in my PhD thesis not so long time ago. So I would like to consider something called reversibility. So I would like to understand whether a translation flow forward and translation flow backward are the same. So I'm so I told you that I'm going, my translation flow, I usually consider vertical upwards with a unit speed. But okay, so what would be the inverse of this action? Would be, okay, go downwards with a unit speed, right? And basically I'm asking a question, okay, are those flows the same flows? Okay, and turns out, mathematically what it means, it means that there exists a Lebesgue measure preserving automorphism S such that it conjugates those two flows. The conjugation means exactly what is written. So if I change my point of view, right? So if I change my point of view, I'm seeing, so I see one flow, I change my point of view, and I see another flow. This is how you can see it. So I'm asking if I see a flow forwards, if I do something, I can see the flow, I can see the flow backwards. This is what is written over here. And actually, many natural examples of flows are reversible. And the example I want to give to you is the flow when the permutation that we considered that created the surface was actually a symmetric permutation, which means that first goes to the last, the first interval goes to the last interval, the second goes to penultimate interval, and so on and so on. And then it's actually very easy to see that the forward flow and backward flow are actually isomorphic, and this isomorphic is extremely easy to see because it's just a rotation by pi. So here you said, so this is the picture that we have already seen, but now imagine this picture, just take the picture, okay, forget about the Cartesian axis, just take the polygon, take the flow, imagine that the arrow now points down, not up, and rotate this picture by pi. And you recover exactly the same picture, right? It's exactly the same picture that you started with. And it's as simple as that. It's really basically the whole proof of the fact that the forward flow and the backward flow are actually isomorphic, right? I'm not saying that the action in a fixed point, in one point forward and backward is the same. I'm saying that maybe for every point you can find a different point for which the action for the backward flow is exactly as the action of the forward flow for the flow that you start, for the point that you started with. I mean, roughly being said, because it's something, it all has to be normalized. And the question that is natural to ask, so I already told you that the permutation, the single surface can be represented by many permutations. So of course, if I take any permutation, if I consider this surface and I take any other permutation with which this surface can be represented, I mean, the flow is the same. It's just a different picture of the surface, but the flow is exactly the same surface, the same flow. So if this one has this property that is isomorphic to its inverse, then the other will also be isomorphic to its inverse. So it will be reversible. Okay, and the question is, okay, but what if we are outside of this class of permutations? What if we consider other permutations, then don't satisfy this, okay? And it turns out, and that, okay, so here, yeah, so it turns out that the expected answer is no, but first let me introduce it. So we have a isomorphism. So isomorphism seems like a strong condition. So being non-isomorphic is going to be rather a weak condition. So instead we are interested in a stronger property than being non-isomorphic. So basically, I'm talking about, I want to consider whether those two flows are disjoint. What does it mean? So the definition is over here. So it's a formal definition which tells you that if you are considering a measure which is invariant by the product action of those two flows, and it projects as your initial measures. So in our case, in Lebesgue to Lebesgue measure on each core of the coordinates, then it has to be a product measure. In some sense, okay, maybe if you are not familiar with the definition, it means that if you want to consider those flows together, then the only option to consider them at once is to consider them independently. So you like to have them both in your one in one hand and another in another hand. You cannot find any common part in some sense in those two flows. You don't get any simplification of considering those two flows by considering them together. You are not doubling information in some sense. Okay. And it actually, here you can see the very simple argument that if those two flows if we have two isomorphic flows, in my case, forward and backward flow, then it's actually very easy to produce a non-product joinings. And the formula is over here, but I hope that you believe me that, I mean, if I have two identical flows, I mean, basically the information about one flow is exactly an information about the other flow, just modulo changing the point of view. So it shouldn't make a difference, and it's exactly what is happening there. And this is the most surprising thing. So actually, together with Krzysztof Frączek and Thierry Delarue, we proved that if the permutation is actually non-symmetric, or it cannot be, it doesn't depend to this one rosy class of the symmetric permutation, then for a G delta dense, so for a topologically large set of parameters of surfaces, the translation flow is actually disjoint with its inverse. So moving forward and moving backward are completely different things. So basically, as long as your combinatorial data is more, it loses the symmetry. If you lose symmetry over there, you lose symmetry on the level of the flows as well. So it seems that, right? So we know that the rotation by pi doesn't work, but maybe some other natural automorphism would work. But no, it wouldn't work, right? It wouldn't work. But actually, simultaneously, surprisingly, even if you consider the permutation that is not symmetric, still by some degeneration of your parameters, I don't want to get into details, but still you can find a dense set of parameters for which the flow, even though the prevalent set of flows of translation surfaces gives you a non-reversible flow, there you still have quite a lot of flows that are reversible. Okay, we would like, so one of the questions that I'm also interested in, but it's still not solved is whether we can do it, we can replace the topological largesse with measure largesse. So if this remains true for the full Lebesgue measure set. Well, I mean, this is not known for me, at least now. Okay, but also I would like to, okay, so we have flow that is, we have a large family of flows that are not isomorphic to their inverses, but okay, instead of, for example, so I told you that I'm moving with the unit speed, okay? I don't want to change the uniform speed, but why not move with the speed, say, instead of 1, say speed 2? Why not? Okay, so I'm moving, everything stays the same. I'm moving in the same direction, I've got the same orbits, combinatorically everything stays the same. I'm just, instead of moving with the speed 1, I'm moving with the speed 2. It seems that those flows have to have a lot in common. But actually, no. With Adam Kanigowski, we proved that if you, for any permutation pi, you can find still a topologically large set of parameters such that the flow TPT and TQT for any speeds, rational speeds, P and Q, those two flows are disjoint. What we actually proved, this is not written here, we proved that they are spectrally disjoint, which is even a stronger property than being disjoint. It means that they even like there is no observable on which they act in a similar way, which seems that they have absolutely nothing in common apparently besides, I mean, those things that I already listed. Okay, and here I can also tell you that in the same paper we prove using the same methods almost, and that actually if you consider interval exchange transformation and we assume something about the permutation, which tells you that you have two intervals which basically travel together. So you have so your permutation takes two of the intervals in the upper curve and just shifts them together by the same amount. Then actually all the iterations, all the different iterations, so you can, for example, act by your interval exchange 2 times and 3 times. Then you get that those two for typical parameter, and here it's really full Lebesgue measure set of parameters. You get that those transformations are disjoint, and here it's also actually spectrally disjoint. Okay, so if you're familiar with the notion of spectral disjointness, then this is what we proved. Okay, so yeah, so this is one of the problems that I'm interested in. Okay, and now I will briefly remind you, this was probably said already in the seminar many times, but let me remind you, what does it mean for a flow to be ergodic? Okay, so it's a ergodic theory, so it must be an important notion. So it somehow describes to you, it's a notion of indecomposability of a flow. So you cannot divide your flow into two sets on which your flow acts independently. Mathematically, it says that if you have any Borel set should be B. So if you take any Borel set B such that this is the definition for the automorphism, so sorry, so there should be T, not -1, here should be TT for every T. So if the measure, you take the flow B so you take the set B and you flow it for every T B, and if you stay always inside the set B, then we say that the flow, if you have such a set, then the flow is going to be ergodic if for all such sets they are trivial, which means that either they are invisible for the measure or their complement is invisible for the measure. So it's a null set in the appropriate measure. So what about ergodicity for translation flows? Well, this is a very classical theory already. So it was proven actually in the 80s that they even proved that not only for almost every parameter, the translation flow, by they I mean Beach and Maser, is actually ergodic. They actually proved that it's uniquely ergodic, which means that Lebesgue measure is actually the only invariant measure. Because usually systems can have more than one invariant measure, and we can consider those measures separately, but here there's nothing to consider. Okay, so now the question is, okay, so we got this. What can you do? What can we do besides? So if this is done, so what can we ask for? Okay, so what we can do is, okay, so all our surfaces were nice and were finite, right? I said in the beginning they want finite because it's easier to deal with. But okay, what if I want to make my life harder? Well, okay, then let's forget about this finite thing and let's just consider infinite translation surfaces. Okay, so I want to consider translation flows on infinite surface. By infinite, I mean that this Lebesgue, you can think that this Lebesgue measure is actually an infinite measure. Okay, and it is known that in general the studying dynamical properties for many reasons, but the finiteness of the measure is really helpful in studying many properties, and many theorems fail in the infinite regime. However, it makes it even more interesting, right, to study properties in the infinite. More interesting if it's harder. Okay, so what are the example of translation flows or billiard flows? Because the next one's going to be a billiard flow that we can study. So we consider the so-called Ehrenfest model. So you take a plane and take every point that is given by parameters of Z2, and in the center of the Z2 put an identical rectangular obstacle, okay, like in the picture, and make them identical, and play billiard in this infinite picture. Okay, so we have this periodic set of obstacles, and play billiard in this picture. Okay, and yeah, and you play this. You do exactly the same thing. So you abide the rules of the angle of reflection being equal to angle of incidence, and you ask, okay, and you can do the same thing. I mean, you got 4 directions, and you can unfold this infinite picture. I don't have a picture for that now, but okay, we can think of it. You can, and you have some gluings as well, infinitely many gluings, but still, everything's nice. And you can ask, okay, what about ergodicity? So we know that we already have the result for the finite case. So what is the result here? And it turns out it was a very surprising result by Krzysztof Frączek and Corinna Olcigrai, that actually for almost every direction, this billiard is not ergodic. It actually has a quite complicated structure of ergodic components, meaning that you can, ergodic component, I mean, it's like you can ask yourself what are the minimal invariant subsets of for the action of such flow. It's to be simple, and it turns out that it's a very non-trivial result. But this already tells you that, okay, ergodicity is not given for free, even in relatively simple picture. Okay, but okay, so this is the result of Krzysztof Frączek, but what am I interested in? Okay, so maybe let's try to construct examples where we still have, but still nice examples. Nice examples usually means relatively simple examples, and in which we have ergodicity. And the recipe for constructing such an example is as follows. So consider a translation surface with the one that you saw already, so given by a symmetric permutation. Parameters should be like some generic set. Okay, so pick your favorite parameters for now. Later we will describe it more. And consider the center of symmetry of this surface. So when we rotate by pi, we have a center of symmetry. Okay, and now take not the interval that starts from 0 like before, but consider the symmetric interval which is centered at this point. And it exactly has the same, still the length of the interval of length 0, the one that you constructed before. So we get the same length of the interval, and just denote its left half by -1 and left half by +1, and the right hand side, right half by -1. And then take, instead of considering one copy of the translation surface, take this whole picture with this interval and consider z copies. I said index copies, so just take copies and give them number. Give that number n, okay, from the z. And and do the same thing. Consider the translation flow, vertical translation flow, and but now we produced things which people usually call slits. So now whenever we are passing through the left hand side half of our interval, we go to the copy with the index 1 larger. Whenever we are passing through the right hand side copy, we go through the index through the copy of through the one of the copy with the index 1 smaller. Here is the picture actually. Okay, so you can see my orbit starts in the copy index by -1, right? Now I'm hitting the red interval. The red interval tells me go to the copy with the number 1 bigger. So what I'm doing, I'm traveling to my copy, which is in the 0th copy, because -1 + 1 is 0. And then I travel in the 0 copy. Okay, I travel in the 0 copy until I hit my interval again. And then in this case, I hit my interval now I hit the blue interval, and the blue interval corresponds to the number -1. So -1 tell me, okay, now go to the copy -1, 0 minus 1 is -1, so I return to my copy again, and so on and so on. I can continue this infinitely. So I consider, so now my translation surface, it's not a single, in this case, octagon in this picture, but it's infinite copies of octagon. And I've got this flow, which is basically, you can think it's like a covering of it's like a cover translation flow on the single copy, but it can go through many copies. Yeah, but does it, right? So do we maybe have, for example, just 2 copies that play, like in my picture, I just showed you that this orbit basically went from -1 to 0 and from 0 to -1. So maybe it's always the case. So it's just 2 copies playing with each other. No, but no. So this is my one of my latest results with Frank Trujillo. So we proved that for almost every set of parameters of the initial guy, so for the initial translation surface, the flow constructed in such a way is actually ergodic with respect to the infinite Lebesgue measure. So you cannot divide your space into some subsets of positive Lebesgue measure on which this translation flow acts independently. So in particular, you know that from whatever points you start, if you wait long enough, you will get approximately anywhere you want. For example, this is one of the consequences here. Okay, so in any copy, so from copy 0 to copy 1000, maybe you have to wait a long time, but you will get there. Okay, so this is one of our results, and yes, I see that my time is. I prepared some things, some sketch of the proof. So I just leave it over here. If you want, you can read it, and I will use my last minute to tell you now what are the other problems that I'm interested in. So I would like to go beyond the symmetric permutation regime in the previous picture. So I would like to see if the same result could be proven. We are really exploiting the symmetry in our proof. I would like to see if it's still true. Again, what if the permutation is not symmetric? And also what another part that another direction I'm working with. So this is my project with Erwan Lano, which we want to study what happens if we add more slits, and those slits are randomly anywhere on the surface, and what will be the results over there. But yeah, and there's also other flows that you can consider on such a surfaces, something called like locally Hamiltonian flows. There's plenty of things to do. You can ask for properties of perturbations of such flows. All those questions are interesting. There are still many open questions. So I hope it was not too basic for you, and I guess I will stop here. Thank you.
Thank you for your talk. And now we have time for some questions. Are there any questions? So, okay, so maybe now I will ask a question. So, you know, if you switch from a rectangle to a pentagon, yes, you obtain something like this Cauchy charts, yes, when you integrate, let's say, a square root, yes, on the complex plane.
Yes.
Yes, here the number is 3. You have to have 3 coverings.
Yes, so it's like you're integrating like a cube, basically, not the square. Cube root, basically. So if you want...
Yes, like a cube root. But okay, for hexagon again, yes, we have a periodicity. For 7, 8, so what is the formula for the number of coverings?
This is a very good question. So I cannot give it on the top of my head, unfortunately. Because the issue is that in the case of pentagon, so you saw this, so depending on the number of sides of pentagon of the polygon, so what can happen is you saw that in my translation surface picture, some vertices are getting glued, and we'll get one copy or 2 copies. One vertex, 2 vertices or something. So in the case of pentagon, it was 1 vertex, and it's like you can see that there is like this one vertex. But in the case of the so it will depend. Okay, I will have to take a look into that, but in my opinion, so if I remember correctly, it depends on the oddity of the number of sides of your regular polygon. And then if the number is odd, I think it's just going to be the smallest integer, which will, if you take an angle of your polygon, that would give you a multiple of 2 pi. And in the case of the and I know, I think it's it. So it's the smallest integer, which gives you the number of the. So you can find a formula out of it. So it's going to be the smallest, because you need to make a full rotation around this vertex. So you will make this full rotation when the sides is actually going to get back to itself. So I cannot give you the formula on the top of my head, but it's this. So you just have to take your angle, rotate it, and take it as much as you need to get a copy of 2 pi, because this would mean that you returned to your initial picture. Okay, so we can compute it probably. I could compute it as well, but I
yes, and you know, obviously, you know, they should produce these billiard tables in the shape of pentagon. You know, it will develop people's imagination better than this rectangular ones. And but I have also idea what in the 3-dimensional case. Yes, of course, if we have just a not know the name, yes, but three-dimensional rectangle, yes, then of course this is periodic, yes. But let's say that we switch, let's say, to dodecahedron, yes, to the platonic solid, yes. So this is regular solid of 12 faces, yes. If we will also try to do it by these coverings, Do you have any imagination if we can do it, and what will be the multiplicity of covering?
I have no idea. As far as I know, even already when we have the covering, it's already not so easy to study the properties, like dynamical properties. I think it's still a fledgling branch of the dynamical system, and unfortunately, I don't know. I don't know actually even who. So I could look for some people. I didn't study it. I don't know. Mm, yeah. Sorry. No, I have no idea, and I don't want to lie.
Yeah, so it's interesting, how hard it will be if we go from D2 to D3.
Probably harder, way harder. But I'm sorry, I cannot answer to this question. I don't know the answer.
Okay, but thank you for your answers, and maybe some other people would like to ask a question. No other questions? So, well, if there are no other questions, so thank you very much for your interesting talk.
Thank you. Thank you for everyone's attention. Okay, goodbye.
Bye.